Well, hello there! I hope you're feeling amazing today and that you're feeling as excited as I am about our today's topic. Because today we are talking about floating point numbers. 3, 2, 1, go! As usual, we are going to talk about floating point numbers in reality. Okay, this should not be so difficult. We, as humans, cannot basically explain everything that's happening around us using just integral numbers. If you do not know what integral numbers are, please take a look at the previous 2 videos I released. Everything will start making much more sense. Let's take a real-world example. You have 2 friends over, so there is 3 of you, and you only have 2 apples. But everybody wants an apple, right? And you cannot share them with using just integral numbers. It is impossible to share 2 apples amongst 3 people without using real numbers. When I say a real number, I mean a number that's not whole, a number that has a part that is after a decimal point. And this is where floating point numbers come to the rescue. Floating point numbers allow us to represent numbers that have a part after a decimal point. Because we need those in real life, as I just explained in our previous example. In Rust, but basically in all programming languages, floating point numbers are always signed. You can always use them as both positive and negative numbers. So the first bit is always reserved for the sign. Exactly the same story as for signed integers that we covered in the previous lessons. And finally, floating point numbers come in 2 main flavors in Rust. And we have 32-bit option and also a 64-bit option. And you're the only person that's going to decide which one you want to use. Okay, I want you to be aware of a single fact, and that is that floating point numbers are a bit more complicated than integral numbers that we covered in previous lessons. And that is why I'm going to film the next upcoming lesson that's going to be dedicated just to memory representation of floating point numbers, because I want you to understand how these actually work under the hood. Okay, now that we know the basics about floating point numbers, I think we can extend our knowledge a bit. We can step up the pace, so to say. In Rust, default type for floating point numbers is 64-bit version, not 32-bit. As was the case with integers, if you remember. You do not trust me. You're skeptical about this. Okay, let me show you. Ta-da! We're in our Visual Studio Code. And now, I will show you all the stuff about floating point numbers, the basics about floating point numbers in action. The first thing I feel like we need to cover is going to be how to tell our compiler that we want to store some whole integral value inside of a floating point variable. To do that, we just need to add a decimal point followed by a 0. Because if we do not do that, the compiler is just going to think that we are working with integer number, not a floating point number. So we need to let it know somehow that it's a floating point number. In future, you will be able to figure this out when we cover literals, but until then, this is the only way you can do it. Great, let's cover it in action. So, we are going to do our standard procedure right now, and we are going to open a new project and our main RS file. And when we have done that, let's create our first variable called our first float variable. And to show you that I'm right and that everything is working as I explained it, I'm going to assign 12 to it, without a decimal point. And when I save the file, you will see that basically compiler infers that this is i32 data type, which is the default type for integral numbers. And to tell the compiler that we want to use floating point numbers, we just need to add the decimal point and 0 And when we save the file, you will see that compiler has inferred the type, and right now the inferred type is F64. I told you so! It's not F32, it's F64, which is the default type for floating point numbers in Rust. And now, if we want to create a single precision floating point variable, I mean F32 variable, we have to be explicit about its type. We need to specify that its data type is going to be F32. So to do that, let's create another variable. And let's name it our second float variable. And inside of it, I'm again going to put number 12, and let's try saving it without a decimal point. When I do this, we get a red squiggly line under number 12. And that is because we did not add a decimal point, which is a required thing for our floating point numbers. Even though we told our compiler that we are going to assign a F32 number inside of it, it doesn't matter. It requires us to add the decimal point and to add some decimal value to it. So let's do that. Let's add the decimal point followed by a 0 again. Great job! So now, let me open my project. I kept this project in secret. I developed it for years. I'm just kidding. Okay, here I prepared a bunch of stuff that I do not want you to observe while I'm failing at writing it down. So we're going to do exactly the same thing as we did for our integer numbers. We're going to print out the ranges for our F32 and F64 data types. And now let us run cargo run command. And when we execute it, you can see that we just get a bunch of zeros. That is because our floating point data types can represent huge numbers. And as you can see, F64 is a really ginormous number. It has 309 digits. Trust me, I know it's 309, but I will show you why. So let's start from F32 min and max values. The range for our F32 data types is going to be from something like minus 3.4, followed by a few more digits, times 10 to the power of 38. So 10 to the power of 38 is basically 10 times 10 times 10 and 38 times, like that. So basically it's 1 followed by 38 zeros times 3.4. And that is a huge number, and I have no idea how it's called. I mean, for example, 10 to the power of 9 is a billion. So this is 10 to the power of 38. So 29 additional zeros are here. And the maximal value is going to be again 3.4 something 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 times 10 to the power of 38. So this is our range for F32. And when it comes to F64, our range is going to be from minus 1.7 something 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 times 10 to the power of 308. Yeah, minus 1.7 times 1 followed by 308 zeros. That is why our terminal here is filled with zeros, because there is 300 and something of them for each value. And of course, the maximal value is going to be all the same as the negative value, but positive. Very simple, right? And yeah, that's it. We just covered floating point numbers in action. Welcome back! And now that I got you here, it's time to talk about another very important thing to have in mind about floating point numbers. And that is, you should not compare them. You should not try to compare two floating point numbers in almost every situation. You should always try to evade this scenario as much as possible. It's not a problem to compare two integers. It's not a problem to compare booleans or characters or anything like that. But for floating point numbers, you should definitely pay so much attention when comparing them, because they have a limited precision. And After we cover our upcoming lesson where we are going to explain how floating point numbers work under the hood, it will be much clearer to you why am I saying this. But the basic premise is the fact that they have limited precision. You cannot represent numbers with perfect, unlimited precision. Okay, so the 32-bit version of floating point numbers has about 7 digits of accurate results. So you can be sure that about 7 digits are going to be 100% accurate in most situations. And for the 64-bit version of floating point numbers, that number is going to be 16. So for the 32-bit, we have 7 accurate decimal digits. And for the 64-bit version, we have 16 accurate digits. So every digit after the 7th and the 16th digit in respective floating point number data types are not going to be 100% accurate. And that is because of the fact that we are using a binary number system to represent these numbers. And we are working with decimal numbers. So basically, we cannot represent every decimal number with complete accuracy using binary numbers. We are just limited. And because of the fact that we are basically thinking in decimal number system, we can make mistakes when trying to compare floating point numbers, because something will be intuitive to us to be equal, and in reality, when we convert that to binary, we will not get the same identical result. So the main purpose of this segment right here was just to bring your attention to this fact. Of course, if you have any questions or concerns, please feel free to reach out to me in the comment section of this video, and of course, I'll try to explain everything in my powers that you might struggle with. And now, before I end this video, I would like to add another page here so you can use it as a future reference. On this page, you can see the basic ranges that you can use for floating point numbers for both 32 and 64-bit versions of it. So if you for some reason need to remind yourself, you can always come back to this video and see what is the basic range that you can use floating point numbers for. So this is basically something like quality of life improvement. I think that we finally managed to cover all the basics about floating point numbers. I hope that this video was very useful and that you thoroughly enjoyed it. And of course, if you did, I would really appreciate if you could subscribe to this channel and like this video, because it will certainly help us grow, both me and the channel. So thank you in advance for helping us out. In our next video, as I promised, we will be taking a deep dive into floating point numbers and their representation in the memory. So we will be learning how our compiler and our CPU are basically working with floating point numbers, and you will learn all about it. So if that sounds interesting to you, please feel free to join me on that journey. Have an amazing day and goodbye!